Good day, everyone. I am Ivy Ludam Luimantawil, and my task in this morning is to continue the report of Miss Justin Kanha, which is the common ion effect and the proteins. So, when you hear the word proteins, what comes into your mind, or what do you think proteins is all about? Well, this morning we will know if what is proteins and what are the functions of proteins.
So, proteins are made up of building blocks called amino acids. There are about 20 different amino acids that link together in different combinations. So, our body uses them to make new proteins such as muscle and bone and other compounds such as enzymes and hormones. So, it can also use them as an energy source. Some amino acids can be made by your body. There are 11 of these and they known as non-essential amino acids. And of course, we have 9 amino acids that our body cannot make. And they are known as essential amino acids. So we need these to include enough in our diet so that our body can function. So why do proteins fold? So hydrophobic effect compacts non-polar side chains pattern into protein core. Non-specific oil compactions. So when the enthalpy of water increases, the entropy will decrease it. So when we say hydrophobic, it is water interacts with the hydrophobic side chains in unfolded proteins. So it forms ordered ice-like structures that are low in entropy. Second one, we have folding is nucleated by super-secondary structures. The third one, we have intra-backbone hydrogen bonds, amide-amide, form a regular order topology structures. So when we say topology structures, this is the sequence or the arrangement of these structures. So energy change is slightly negative charge, which is amides can hydrogen bonds to water almost as favorably as to each other. Peptide is fully exposed to water when it's unfolded or extended state. So we have here the hierarchy of protein structures. So as you can see in our concept map, we have the proteins and our proteins are composed of polypeptide chains. So when we say the polypeptide chains, these are the amino acids which are linked together. So in our polypeptide chains, it is tremendous diversity of because of the structures. Our proteins has a four structures. So what are those? So first we have the primary structures, the secondary structures, the tertiary structures, and of course we have the quaternary structures. So in our primary structures, this is determined by the sequence of the amino acids. So our amino acids are made of the amino group, carboxyl group, and the R group. And in our R group may be one of the 20 different structures. So the secondary structures from hydrogen bonding between the peptide bonds and the helix pleated sheet. So in our tertiary structures, these are the interactions among the R group and our quaternary structures. These are the interactions among the polypeptide chains. So, our proteins are significant to understand why. Just because it is the nutrition bodybuilding routine of our blood test. So, of course, proteins are diverse in functions. So, the major functions of protein as enzymes. So, enzymes regulate the chemical reactions. Of course, we have here the cell structures, cell movement, defense, transport, communication, storage, and of course, function lost if protein is unraveled or denatured. So we have here the folding protein. So as what I've mentioned a while ago, our protein has four structures and what are those? Again, those are the primary, secondary, tertiary, and of course the quaternary protein structures. So in our primary protein structures, these are the sequence of a chain of an amino acid. So Even protein is determined by the sequencing of the amino acids. The formation and ordering of these amino acids in proteins are extremely specific. So, if we alter one amino acid in the change, it results in a non-functioning protein or what we call the gene mutation. So, the next one is the secondary protein structure. So, in our secondary protein structures, the local folding of the polypeptide change into helices or sheets. So, the folding of the polypeptide chain happens to the interactions between the carboxyl group along with the amine groups of the polypeptide. So, uh, our secondary protein structures has two kinds of shapes formed. So, what are those? We have the helix and the pleated sheet. So, in helix, this is the backbone follows helical structures. The hydrogen bonds with the oxygens between the different layers of the helix, which is giving the helical structures. We have here also the pleated sheet. So in the pleated sheets, this is the polypeptide chains which are stuck next to each other and their outer hydrogen molecules form intermolecular bonds to give it sheet-like structures. So, of course, let's proceed to the tertiary protein. So, in our tertiary proteins, these are the three-dimensional folding pattern of a protein due to the side chains interaction. So, in our tertiary structures, these are the structures that give proteins the 3D shapes and formation. So, after the amino acids form bands in the secondary structures and shapes like helices and sheets, the structures can coil or fold a random. So, this is what we call the tertiary structures of the protein. So, if these structures is disrupted or disturbed, a protein is said to be denatured, which means it is chemically affected in its struggle and its structures is disordered. So let's proceed to the quaternary structures. So in our quaternary structures, this is the protein consisting of more than one amino acid chain. So it is important to note that it is necessary for proteins to have quaternary structures, primary, secondary, and tertiary structures that present in all natural proteins. But the same is not true for quaternary structures. Hence, if a protein has only the first three structures, it is considered to be a protein. So we have here the 20 amino acids. So these are the alanine, asparagine, cysteine, glutamine, histidine, leucine, methionine, proline, threonine, tyrosine, arginine, aspartate, glutamate, glycine, isoleucine, lysine, phenylalanine, serine, tryptophan, valine, and of course the isoleucine. So some amino acids can be made by our body. So example for this is uh, the proteins coming from the food we eat, just like for example, the proteins coming from the apple we eat, proteins coming from the meat we eat. So there are 11 of these and they known as the essential amino acids. And we have 9 amino acids that our body cannot make. And they are known as the essential amino acids. So we need this to include enough in our diet so that our body can function. So we have here the non-essential amino acids. We have the alanine, the arginine, asparagine, aspartate, we have cysteine, we have the glutamate, we have glutamine, glycine, proline, serine, taurine, and the tyrosines. So, in our essential amino acids, we have histidine, isoleucine, leucine, lysine, methionine, phenylalanine, threonine, tryptophan, and of course the valine. So we have here the aliphatic compound. So our aliphatic compound are cyclic or acyclic, saturated or unsaturated, non-aromatic hydrocarbon. So we have here the structures and a functional group. So as you can see, our glycines are under aliphatic compound, and the structure of this is R is equal to negative H. Next one, we have alanine. R is equal to negative CH. And of course, the proline. As you can see, this is the structures of the proline. We have H, OOH, and then NH. So we have here branch chain amino acids. Our branch chain amino acids is nucleate protein folding. So under branch chain amino acids are the following. We have valine, and the structures of this is H3, open parenthesis CH3, 2. We have isoleucine, R is equal to CH, CH3, CH2, and CH3. Leucine, we have CH2, CH, CH3, 2. Next one is the aromatic amino acids. So under aromatic amino acids, we have phenylalanine. So as you can see, the structures of phenylalanine is R is equal to negative CH3. So the functional group of this is a phenyl functional group, which is the benzyl moiety. Next one is the tyrosine. So the structures of these tyrosines are R is equal to negative CH3OH. So a phenol purwick acid pK is equal to 10, or it is a rare conjugate base form phenolate. So a relative rare sites for equations of protein functions by phosphorylation. Next one, we have the tryptophan. So, a planar aromatic or bicyclic indole functional group. So, nitrogen containing pyrrole ring fused to a benzene ring. So, as you can see, we have here the structure CH2 and then NH. Next, we have the basic amino acid residues. So, in our basic amino acid residues, we have lysine. And the structures of these is R is equal to CH2 minus CH2 minus CH2 minus CH2 and minus NH2. This is an amino functional group, which is a primary amine and a good weak base. Next one is the arginine. So the structures of these are R is equal to negative CH2 minus CH2 minus CH2 minus NH. Post in open parenthesis is equal to NH minus NH2. So a planar or a guanido functional group, which is essentially a strong base. The third one is histidine. So the structures of histidine is CH3, HN, and N. So this is an imidazole functional group. So this is a mild weak base in water 7 pH. There is one conjugate acid form for every 10 molecules of base. So we have here the sulfur containing, and under the sulfur containing we have cysteine. So the structures of cysteine are is equal to negative CH2 minus SH. And this is a trial functional group, which is a formic acid, pKa 8 at pH 7. There is one thiolate conjugate base form for every thiols. Next one, we have methionine. The structures of this methionine is R is equal to CH2 minus CH2 minus S minus CH3. And this is a thioether functional group, which is no acid-base chemistry. Next one is hydroxyl containing amino acids. So under hydroxyl containing amino acids, we have the serine. So as you can see, the structures of serine is R is equal to negative CH2 minus OH. Next one we have, and of course this is a primary alcohol. So most common site of this regulations of protein functions by phosphorylation. So the next one we have threonine. The structures of threonines are R is equal to CH, OH, minus CH3. This is a secondary alcohol, a second site regulations for protein by phosphorylation. So next is we have the acidic amino side chain. So under the acidic amino side chain, we have aspartic acid, and the structures of this is R is equal to negative CH2 minus CO2H, and this is a carboxylic functional group. This is a good weak acid based. Next one we have the glutamic acid. The structures of these glutamic acids are is equal to negative CH2 minus CH2 CO2H, and this is same functional group of aspartate. Next one, we have the amide containing amino acid. So under amide containing amino acid, we have the asparagine. So the structures of this is R is equal to negative CH2, negative C or minus C rather, whose in open parenthesis is equal to O, negative NH2. And this is a polar side chains but no acid-based chemistry. Next one, we have glutamine. So the structures of this, yes, R is equal to negative CH2, CH2, C, whose in open parenthesis equals O, and of course negative or minus NH2. And this is no acid-based chemistry. Thank you for listening. To God be all the glory.